Hello, welcome to our webinar on how to use an API for electromagnetic analysis. My name is Doug Cragen. I'm a physicist here at Integrated Engineering Software, and I'll be conducting the webinar today. API stands for Application Programming Interface, and many of you will already be familiar with this, but for those who aren't, let me just explain that an API is actually the critical thing that developers use in order to develop apps like you see all over the web and on small devices. For example, if you said you wanted to develop something for Twitter that would build off of their very large user base, then you would go to the developers part of the Twitter website, and the very first thing that you would see in big bold letters is how to get started with their API. Similarly, if you wanted to develop something for Facebook, the developers part of their website starts with learning how to use their API. If you wanted to build an intelligent store that interacted with the Amazon product catalog, you would learn their product advertising API. Likewise, if you wanted to interact with Google Maps on your website, you would learn the Google Maps API. And finally, in the lower left corner here, Android phones, Android tablets, and so on. If you want to develop something for these, the first thing that they show you as a developer is their API guide. So of course we could carry on with more examples, but you should get the idea. The API is the thing that fundamentally lets somebody build off of a powerful environment that already exists. So the question is, what use might there be in electromagnetics for generating apps using an electromagnetic API such as we've now put into the integrated software? The first type of app that I would suggest is custom tools that will automate tasks that you commonly perform. For example, if there is a geometry that you normally create, but with it some variation so that you can't just copy the same geometry from model to model, you can create an application which will generate that geometry on demand with the variations that you want. Similarly, if there's analysis that you commonly perform because of EMI, EMC types of issues, meeting government regulations for field strengths and all this kind of thing, you can create an app which will automatically perform that analysis on demand rather than having to do it live yourself in the software. You can also create EM simulation tools that interact with other tools, and that's where an API is really more powerful than simply a scripting environment that you might have within the software. With a script, yes, you can do the things I discussed above. You can create a script that will prompt you for parameters to draw your geometry, for example. But let's suppose that what you want to do is to use the optimization code in MATLAB in order to keep modifying your geometry. Well, a scripting language built into the software won't enable you to do that. But either from MATLAB or from a third program, you can link to everything that has APIs available and take direct control. So you could write a program which would go send commands to MATLAB, get information back, send commands to our software, and go back and forth. And you could do the same thing for system simulation and so on. A very common use of the API by our customers right now is to create programs for use by non-experts within an organization. So there may only be a couple of people with the expertise to really use our software in the full sense of the word, but those people can create programs that are useful by others. And In some cases, it's even been put onto the shop floor where, for example, somebody says that I have a requirement where I need to fit this device into a box that's smaller than what it fits in right now. So I want to see what will happen if I just trim a little bit off the top of it. So with a program that's been created for that kind of purpose on the shop floor, the person can type in the parameters that they want to use and get an answer back by an app that invokes an integrated program, performs some analysis, and then gives an answer back like, no, the force isn't high enough, no, too much field leaks out, and so on. Or maybe gives an answer like, yes, that passes, or this is marginal, it needs to go to R&D for a more thorough analysis. For people working in niche areas, there's the possibility to create programs that coupled together with our software you could go out and sell. So this could be useful within consulting work, but also within niche areas. For example, if there is a device that you know how to simulate, and you know that there's a small number of people, like maybe a dozen people in the world, who would pay a lot of money to be able to do that kind of simulation, you do not yourself have to invent the back-end reliable electromagnetic solver. All you need to do is to write the front part of it, which performs the tasks of interest, and rely on one of our products to do the back part of the calculation. So we are interested in talking to anybody who is wanting to do this. So what are the things that you need in order to create an API app for electromagnetic purposes? The first thing that you need is general purpose electromagnetic software that has an API. The next thing is that you're going to create an interface somewhere where the user sets up the task that they want to perform, and you need to write code somewhere that's called by the interface. So there's two common methods for this. One method is to use a development environment like VisualStudio that produces a standalone program. In this case, the user will see something that appears like any other program on their desktop. They can have shortcuts, they click, they open it up, the program sits there, and they're just interacting with that program. Another way of doing it is to work in environments that have a scripting interface, such as MATLAB, Mathematica, or Excel. In the case of Excel, for example, people very commonly have Excel and know how to use it for doing spreadsheet sort of work. And lots of people have all their data sitting there. They do all their plots with Excel at the end. So you can make it the work much more convenient by writing a macro which will read data out of the Excel spreadsheet, invoke our software, perform some commands, get feedback from the program, and then put it back into the Excel spreadsheet. So we will provide 6 examples of using the integrated API, and we'll then do one live demonstration as well of the example that you're looking at right now. What this example shows is the 2 program design windows in VisualStudio for creating a generic insulator model simulation program. You can see what the program looks like on the right-hand side, where it's being created in the visual design window, and on the left you can see the code that interacts with the form. When the user actually runs it, they're not seeing anything to do with VisualStudio. What they're seeing is a program called ELECTRO Insulator Project, and over on the right they're seeing the integrated ELECTRO program running the analysis as requested. And in this case, 4 different scenarios have been run, so the chart has been updated 4 times and the data sheet has been updated 4 times. And all of these examples are available for integrated users to use as templates for other work. So in this case, you have a template for doing things like creating a live updating chart and a data sheet, which you can save externally. The next example shows what's called a Hallback Wiggler, a device that's useful in a lot of particle beam applications, which works by changing a magnetic field in an oscillating fashion by having 2 sets of permanent. What the user would see is the Excel spreadsheet that you see on the right. But what you would create along with the spreadsheet shown on the left that the user wouldn't see is some Visual Basic for Applications code that works as a macro within the Excel spreadsheet. So when the user has filled in some parameters for their wiggler and clicked Run, then you will see the window as shown here. The Amperes program will construct the Hallback array and solve it, and the macro will inquire field down the center and create a chart and a graph within the spreadsheet that the user is looking at. So we'll use this example to break down in some detail what you're actually doing. The spreadsheet has a couple of GUI options sitting in it, one for choosing the unit and one for starting the analysis. And these are linked to a couple of macros. So when you change the unit, it invokes the Apply Unit macro. When you click on the Run button, it invokes the Make Model button. And I also point out in a green box down at the bottom, this particular spreadsheet has been named General for reference from the macro. So when you look at the macro, the first thing that you see is a bunch of variable declarations that will be used within the code. The next thing in the green box at the bottom, you see that the Amperes program is invoked by calling the Windows registry and looking for something called IES.document. It is then referred to within the code as OBJ. There is a small time pause given just to make sure that the code doesn't get ahead of when the program's even open. The next part of the code is to read data out of the spreadsheet. So in the red box, you see the code which it says go to the spreadsheet, look at the tab called General, go to the cell B3 and read the value and assign it to the variable called width. And if you look on the right, you can see in the spreadsheet itself on the General tab, there is the B3 box, which we've also labeled width in the spreadsheet. The green box, it shows a couple of calculations performed for convenience, and then the main part of the code begins. The first thing is to create the geometry according to the specification, and here is where the OBJ comes into effect. We invoke a function in Amperes from a command that looks like obj dot and then whatever command we want to call. So in this case, geometry create line, and then passing the parameters computed at the top of the for loop. We create 4 lines, then we define those 4 lines as a surface. We sweep the surface to create a volume, then we put material in the volume, then we assign a magnetization direction to the volume. We do that for the top and the bottom magnets, and then we carry on to the next pair in the for loop and so on until all of the geometry has been created and assigned the appropriate physics. Once that is done, the next thing is to invoke the solver. Again, the format is simply obj dot, in this case a routine called solution run solver. Another routine is called just to make sure that we're in static mode, since permanent magnets are static fields. In the green box you see a for loop which looks for a location a little bit to the left of the array and a little bit to the right of the Hallback array, and then subdivides to inquire the field at points along a center line. So the field is computed and values are put back into the spreadsheet. When that for loop is done, then the cells that were actually filled with the code are passed to the chart so that the chart knows which cells to show. So again, when it's completed, what the user sees is the Ampere's program with the specified Hallback wiggler constructed, and an Excel spreadsheet with a data table filled in, and a plot of the magnetic field running down the center. The next example doesn't rely at all on building the model. It's an example of a post-processing tool created. So this came from a user request that said after every single simulation we need to produce plots of B normal and B tangential on circles along the axis. And of course they knew how to do this interactively, but we're just looking for a convenient way of doing it automatically. And this is very readily done, again with an Excel spreadsheet, by simply providing inputs for the distance along the axis, the radius, and the number of points you want. And I created this with 128 points as the default, anticipating that something like a fast Fourier transform analysis may be wanted. But once the user clicks the run button, the program will simply go and compute the locations of X, Y, Z. It will then inquire the field components, and it will then calculate B normal and B tangential from those field components. Then it will update the chart. Here is another example mentioned at the start. In this case, a custom drawing tool for making polygons of arbitrary size, center, and number of sides. So with these polygon generator tools, we will draw the polygon according to the numbers entered on whatever is the active plane. In a 2D program, of course, there only is one plane. In a 3D program, we can choose from multiple planes and even define working planes. Another common interest for any kind of scripting purpose is the idea of doing some tolerance testing by performing random variations. So these can be for any aspect of the model, because in the real world nothing is completely ideal. There's tolerances on sizes, tolerances on material properties, and so on. So what people are often looking to script is some randomization that will give them an idea about how much effect different tolerances will have. The chosen example here is a program which works with the Lorentz particle ray tracing. And if we were to launch a particle from the same location at the same energy repeatedly, of course it would always follow the same path. But in the real world, particles will have some random variation in their energy, and they will start from randomly varying locations. So what this script allows somebody to do is to play with those random specifying initial conditions for a particle. If they like what they see in the table, they click the Run in Lorentz button, and the program will then call Lorentz, open a predefined model, and insert all of this data into Lorentz, launch the analysis, and then report back the conditions of the terminal point for the rays that were computed. The final example shows a very simple kind of optimization. In this optimization, it is assumed that we have constrained a problem such that our only room to play is with the shape of the pole faces. So the objective is to get a uniform 500 Gauss field in between the pole faces along the black line shown. So the initial result from using flat pole faces shows B fields of 450 to 485 Gauss. So what we want to see then is if there's some way to change the shape of the pole faces, which will make that more uniform and pull its value up to be 500. The approach that was taken was to say, let's divide the pole faces into 6 sections where there is a point that can be pulled in order to change its shape. And we'll also divide the reference line where we make the plot into 6 sections and create a one-to-one correspondence. So that when I run an analysis and inquire the field at those 6 points, if it's too high, I say I want to move the corresponding pole face a little further away. If it's too low, I want to move the corresponding pole face point a little bit closer. So as we do this, what you see is that we oscillate around but do converge in to having these points set at 500 Gauss like the goal was. So this particular script, it lets you look at an updated chart, and then whenever you click Run, it'll do an assessment on the existing data and do some pulls and resolve the model. So by the time it's done, this is what you're looking at. The actual pole faces have a wiggling shape that I would have personally been hard-pressed to have predicted. And the chart now shows that the field is in fact at 500 Gauss, very closely at my 6 reference points, but it does of course oscillate around that value, and it oscillates around by about 0.4%. So this project was successful in its goal of making the average 500 and reducing the spread of the B field, but of course whether this is good enough for the application intended would rely on the application. And it may be that this in fact it solves the goal, or it may be that after doing this analysis you would say, well, maybe I need more than 6 control points, maybe I need to release some other constraints in order to achieve the goal. So in summary, the API provides electromagnetic simulation far more power than simply adding features to the software itself. We of course are always striving to add more useful features to the software in a way that doesn't generate bloat that makes the software more awkward for the user. It's a very delicate balancing act for a company like us. But what you can do as a user is you can always make very targeted tools now to perform the exact tasks that you want. We've shown examples in a few areas that we know people are interested in creating small apps for their electromagnetic analysis. We could have included more examples given time, and especially examples showing more interaction with other programs. So for example, creating mechanical custom coupling, creating custom to simulator, system simulators and circuit simulators, or interfacing with other API-enabled programs in general. So what I would like to do next is to simply show an example live running with the API. And this is the very first example of the 6 that we showed. Here you're looking at the VisualStudio design window for the generic insulator model. So if we look here, there is a toolbox where I can simply pull into my design sheet all kinds of objects that you're familiar with, picture boxes and check boxes and buttons. I can pull them in, as you see here, change their properties, and then go over to the actual code and write code that interacts with those objects. So it'll read values out and perform functions when you click on boxes and so on. Very similar to the Excel case, we have a link to the integrated program. In this case, it's _document. After that, we have a dot and then the command name. So at this point, it looks exactly the same regardless of what program you're in. It's only the initial part that really cares whether you're working with Visual Basic or C# or something else. A nice thing I personally like in VisualStudio is that when I start typing, let's say underscore, you see it pulls up a set of underscore options. I then type D and it recognizes _document. So I click enter. Now I put in the dot and it recognizes all the functions available in our API. So if I start typing here, for example, now I have a list of physics functions because I started with the letter P. So if I click on one of these, now I have the function filled in. I start with the bracket and it tells me what variable it's looking for. So the convenient thing about working in VisualStudio that I really like is that I don't need to know all these function names. What I need to know is the structure for how the functions were named, but the program actually fills in all the details for me as I start typing. So within VisualStudio, I can now start the program, and you see the program that opens up looks just like the form that I had designed. And in fact, I can now close VisualStudio completely because what I'm doing is independent of it. If I click on the Run button, then that will call the integrated program ELECTRO, and within ELECTRO it will build the insulator according to the specifications, solve it, create streamlines in this case that it's been requested to create, find the maximum field and add that to the chart. So if I was to live start changing some things like the number of sheds and click Run, every time I do that, it will redraw the structure and it will update my chart and my data table that I've put in. So with a tool like this, you're able to interactively keep reconstructing your geometry and looking at results of interest that come back. The example is also made with an autosave option here so that you can see we're on case number 3 now. All the cases that were created are actually being saved to the disk so that I could open them up and study them separately later. So that finishes the formal part of this webinar. I'd like to thank you for attending.